Okay. So, example on chain rule, okay, to make sure that we can apply the method. Okay. For example, if we have y equal x power of 3 minus 1, 100. Okay. We want to have dy over dx. First, we can imagine this as the outside functions, and this is the inside function. Or you may suggest to have the composite, if you want, like f of g of x. Okay? And you can see that the f is actually similar with your questions in the quiz, right? So you can have f of x is x with power of 100, and g of x is the inside function, which is x with power of 3 minus 1. Okay. Now the idea here, using the chain rule means we need to derive the whole thing, means the outside functions. Okay. So we derive this, or if we take this a little bit here, so we have f prime x is actually 100 x 99, and g of x prime is 3x squared. Okay. Now the chain rule will be, because g will be inside functions, g will be inside of f, then we can write this compositions to be 100, and then g of x, we write x cubed minus 1, 99, and then multiply with the g prime. Okay. Or we can directly write 300 x squared x cubed minus 1, 99. Okay. This is, I will take slowly here. So which means we have this, and we can imagine how the functions can be composed. For example, we can have these two. Then the idea of the chain rule, that is, if you have dx f g of x, this will be f prime g of x, and then multiply with g prime x. And then what happens if you have more composite? Like inside the function, you still have the functions, and then inside those functions still has more functions inside. Like a sandwich. Okay. So if you have more, maybe ddx, f, maybe g, and then h, and then maybe w. Okay, like a crazy sandwich like this. What you can do is you can slowly take it one by one. Like you peel onion. You peel the onion for it. So first you can take the f prime. Okay? You can take the f prime. Okay? And then you take the inside one. Okay? But because it still has more inside, it's not directly answered like this one. The top one here, we stop here because there's no other function inside. Right? But here we still have more functions, which means that we can write, because this should be the g prime, we can write in terms of d dx, okay? To give you an idea, okay? Okay. And now we can have this terms to be differentiated one more time, and then one more time over until several times. Okay. So we will have here, we can write f prime and then g prime, and then we still have more ddx h. Okay, this is just an extreme case. Okay, extreme case, and then you can do more up until you get the last function inside. So it's like peeling the onion, like I said before. Okay. So that's the idea for the chain rule. Okay. And actually, you can apply the chain rule in every situation that the function can permit you to do the chain rule. Okay. So most applications you can do chain rule, as long as you know how to derive those functions. Okay. And I think compared with integral that you might find later, derivative is much more easier to do. Because integrations means you need to reverse the derivative. You need to think backwards what it looks like before it was derived. Okay? Okay, if we have another one, if we have y equal e with power of sine x, okay? If we want to know the first derivative, okay. Oh, by the way, we have established before the e, right? So that if you have e with power of x, the derivative is the same e. So if we have e with sine x, means that the whole functions or the outside functions is just e, right? E with power of x. So we can set up f g okay. So if you're still not sure on chain rule, you can take times and look on the compositions, okay? But if you feel confident, you can directly derive. I think if you're already familiar, you can directly derive, and this means that this becomes e sine x and then cos x. Because the f prime still e to the x, and the g prime is cos x. So f prime g of x is e sine x, and g prime is cos x. So we need just to multiply this. Okay. And sometimes you can also take times to make up a functions that may be dy over dt, and you can see the relations. Maybe the question or the problem give you information that this is function of x, and you have x with t, and you can see the connections, right? Or if you want to have another functions that is having another variable that you can think the derivative of it, so it's more like having relations between functions, and you can see the connections. And sometimes it can help you to establish connection. I think it's also helpful to adjust this, and you still need to take the calculus 2. This will be helpful. Okay? This will be helpful to see the connection. Because calculus 1 we only deal with just a single variable, but the calculus 2 is we have the multi-variable. So single variable means that we always see the y is function of x. Okay, because we already see the exponent, because we have established our definition of exponent, there's a general exponential functions, like for example bx. Okay. So we have functions of bx. Okay. Based on the definitions, okay, what we have in previous sections, in previous slides, if we derive b with power of x, it still has the same b with power of x, but it has another constant, that is ln b. Okay. If you imagine b as e, this means it's still the same, but ln e is 1, right? So this is actually the general rule is we have a proportion of a constant ln b. If you remember what we did in the proving with limit, if you remember, we established that it should have the original function, and we have a constant. And we established also the definition of e, right? And then we know that e is a number that can make the limit becomes 1, right? So that's, if we have this e, then this will be just 1. Right? We have some unique property of these functions, that is, if you derive, it's still the same functions. Okay? And it's really helpful, okay? Because if you apply this to all most of the natures, they will have the same proportions. The e number always appear, and it's helped us to look on more analysis, graphics, like populations. This should be having the e. So most of the exponential cases, it will have this e, okay, the number e. So this is the general rule for the exponent. You can also think, okay, the exponent as, you can manipulate the form and take this e and then ln b or this is maybe to make it easy to look at, okay. And when we take this as a derivative, this will appear as itself, and then we will have the dx of ln b, ln bx, and then this will be resulting the same bx ln b. Just another view, but if you think it's much more complicated, then we can just stick with this one. Okay, so that is the general and the general exponential. Okay, for today, I would like to focus, I think this will be the last sections. The section is called 3.5, implicit differentiations. Okay, let's think on a circle that is x squared plus y squared equal 25. Okay, now if we take this into a graph, okay, this is just a normal circle with radius equal 5. So let's say this is the radius. Let's say this is 5. Okay. If we think clearly from this circle, maybe before we start doing the implicit, we can take these sides, okay, these sides on the top circle here. We can write this as we can write in terms of y squared equal 25 minus x squared. And then we can take this as a function, okay, as a functions. Y equal plus minus 25 minus x squared, right? Okay. Now, if we have this plus minus, means that we can separate this circle becomes two semicircles. The positive one will be this on the top, and the bottom one will be the negative one, right? So this will be f of x, positive, and the bottom one we can have negative, okay? And of course, if we have these two definitions, we might have some idea to derive each one, right? We can just derive as usual with the square root, right? We can derive. But then, how do we develop? Okay? If we have some kind of functions like this, we have x, we have y. We want to take the derivative, okay, to take the derivative, and still we need to find a way to derive this as simple as we can, and by doing so, we call the idea of the implicit. Okay, let me just show you this triangle here. If this is 5, okay, if this is 5, and if this is 4, okay, if this is 4, this should be 3, right? It should be 3. Okay. Now let's say we have the tangent here. We have the tangent. And then the tangent, we are going to move around here, around to the left, maybe here. It's still the same 5, right? The same radius. Okay. And you have the tangent here. And then if you look on the triangle, how dy and dx move, or if you look at the tangent, it's moving here. If you see the dx and dy, they will change. Right? For example, this is dx. It seems dx getting smaller, and dy getting longer, right? Okay. But the ratio is still the same, dy over dx. Okay? So dy over dx is still some value, some finite value, but dy is getting longer or getting shorter, or dx also changes. Okay? So what I mean is, if dy getting larger, dx getting shorter. If dx getting shorter, dy getting larger. Why this happens? So that x squared plus y squared is always 5, or always 5 squared. Okay. Okay. Now, the idea here is, because y is not equal f of x. Okay. Although we can take approach that we can have positive, negative, we may have two kind of functions. But still, if you think on the circle, this y is not a function of x. Actually, right? Actually. So we say that y and x is independent. But, okay, what we are doing in implicit differentiation is we are taking this y as a function of x, although it's not. I hope you get what my point is. So, if we have x squared plus y squared equal 25, okay, and we want to have differentiations, so we treat y as a function of x, but we need to have additional content. So if we take this x squared, we're just having a simple 2x. Now plus y squared, it has 2y, and then you need to add dy over dx. Now, how this dy over dx appear? Because we treat y as a function of x. Okay, we treat them as a function of x. I hope you get my point here. And then if you have maybe another example, if we take this, okay, if we take this x squared, still 2x, okay? And now if we have 2xy, means that we have the product rule here. We have a product rule. So we have variable 1 and variable 2. Okay. So we can have 2, and then x derived become 1 multiplied by y, okay? And then plus x multiplied by derivative of y is dy over dx. So it's like fg in a product rule. Let me write here product rule. And then plus 6y dy over dx. And then equals 0. And then if it's asking dy over dx, then we need to solve and find the dy over dx. And then find dy over dx. Okay. So to solve the circle one that we have before, we don't need to take the functions as a positive and negative, and take the semicircle top, semicircle, and the bottom semicircle. We can just adjust our circle and then derive through the implicit differentiation. So we implicitly say that y is actually a function of x, and we can treat y as x, but we need to have connections to dy over dx, okay? As in the chain rule and so on. Okay? And the further informations from this dy over dx, if you need to have second derivative, if you need to find second derivative, it depends on the functions. If this happens to be some rational, like something f over g, then your second derivative will be having the quotient rule. So step by step, slowly, you need to take the dy over dx and then take to the next one, the second one. And if you need to have the third one, you need to take the first one. Okay? So you need to take step by step. So there is no direct results from the function, and then you get the second derivative. There is no direct result. So you need to take one by one, carefully look on the dy over dx, and then you derive another one and derive another one. Okay? So that's the implicit differentiations. Okay, now from this implicit, okay, from this method, you can use this method to check on most of the derivative formula or method. Okay, so for example, if we check the, for example, f of x is ln x. Okay, some of you maybe know that if we derive this, it will be arrived at, we will have the 1 over x, right? But let's just say we have so x is actually e or maybe, okay, we start from just a base number b. Okay, we start from, so let x equal, so we can have a random number b, like a base number. Okay. If we take maybe x on the right to make it more clear, if we take this and derive, remember b with power of x or e with power of x is still the same, but we need to add or multiply dy over dx for the implicit. Okay. So this will be b with power of y, ln b, and then multiply with dy over dx. Well, let me make a bracket. And x is equal 1. And dy over dx will be equal to 1 over b with power of y ln b. B with power of y is x, right? And if your b is equal e, then it is this one, so 1 over x. Okay. So if b equal e, ln e will be 1, right? So this will be equal with 1 over x ln b. Or if you would like to imagine from e, directly e, you can go through this one also. You can derive this. This is 1. This is still e with power of y. And then dy over dx. So dy over dx will be 1 over e with power of y, and e with power of y is just x. So this will be equal to 1 over x. Okay. So every time you derive a variable of y, because y is function of x, you need to multiply with dy over dx. Okay. But remember, if sometimes the problems is maybe making you into some variables that you need to define, you can define any variables as you want as long as it's consistent with the implicit. Maybe it's u, v, anything. Okay. But usually in your textbook, it was always y equal function of x. But it's eventually you can take any variable that you want as long as consistent with the rules in the implicit. Okay. I hope it's not confusing here. Okay, I hope it's not confusing. Okay. So basically, you derive the variable y, and when you derive, you need to multiply with dy over dx. This is normal table. Normal table. So, for example, if you have maybe another variable, for example, dx, ln u, for example. If u is function of x, then we can say that this will be 1 over u, and then du over dx. This is just a function. Or if you have ddx, and then ln, and then a function inside the ln, we can treat this as a chain rule, normal chain rule. This will be 1 over g of x and multiply with g prime of x. Okay. This is just some introduction on the ln and the exponent. We'll be giving you another perspective, okay? Another perspective before we end our lecture. If we have y equal x with power of n, we know this is the power rule, right? We know that this will be having, if you have y prime, this will be n, x, n minus 1, right? But what happens if we are looking into the world of logarithms? Okay? If we take the ln y, and then ln x with power of n. So if you take this equations, if we take both ln remember, if you take the ln here, means that every power have this ln. We can move to the front. Right? So we can have ln y x and ln x. And then if we derive ln y becomes 1 over y and then dy over dx, right? Okay, so that's right. So 1 over y dy over dx, and then this will be n, just a constant n, right? And then 1 over x. And then we can have dy over dx equal, we can multiply y, cross multiplies to y, n, and 1 over x, right? Y itself is x with power of n. So we can have this x to the power of n, and then we have x at the bottom. We can take this as a minus 1. Okay, so we can write n x n minus 1. Okay, so we can take this approach to prove also most of the formula in derivative. You can take the power rule, product rule, any significant formula. Let me just take a look on the product rule for a moment. Let's just say that we have this, and we can take the ln and then take the derivative, and then this will be, and then this ln we can have ln f plus ln g, right? And then derive each one. So we will have 1 over f and then f prime plus 1 over g prime. And then y is fg. Okay, so dy over dx multiplied by fg. So fg f prime plus fg g prime. And then we can cancel. And then we can develop the product rule using the implicit differentiation. Okay, so to prove, we need to add the law. Okay. So this is what I say one of the unique property of the law. It can help you to to include most of the derivative formula, and then you can prove that on their own. Okay? So use the implicit differentiation and using the ln. You can also do the same method with the quotient rule and other formulas. Okay. I think I will just stop until here, and we will see you again next Tuesday. And I think we go to next sections, and maybe a little bit some review on the ln and exponential, because I just mentioned this without any details. Okay. I think we can stop until here.